Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 5, which is Analytical Applications of Differentiation. Today we're doing topic 5.8, which is sketching graphs of functions and their derivatives. Today is a calculator lesson, so you are going to want your T83 or T84. And just some reminders that when we are using calculators for AP Calculus, we're always using radian mode. And if you're rounding, you should always round to 3 digits after the decimal place. Enjoy today's notes. All right, welcome to the second half of Chapter 5. We're in Section 5.8, which is about sketching graphs of derivatives. We've got sort of two main goals for today's lesson. The first is, how do you sketch a graph of the derivative of f prime if you're given the graph of f? And the other being, how do you sketch f if you're given a graph of the derivative f prime? So those are two different ideas, sort of working in opposite directions, and we're going to discuss both of those today. Additionally, as we said at the beginning of this lesson, this is a calculator lesson. We're going to also talk about how to graph a derivative using your calculator. We know that on the AP exam that half of the test generally is calculator allowed, and they expect you to be able to take the derivative on your calculator. So let's start first. The idea here is we want to focus on the slope of f. And the slope of f is going to be the output or the y value of f prime. So the idea here is when we're trying to sketch f prime of x from f, that is what we're thinking about. So focus on the slope of the f function. The slope of f is going to become the y value of f prime. And that makes sense because f prime is the slope of the tangent line, right? That is the definition of the derivative, the slope of the tangent line. All right, so let's see that in an example here. So we have this function f of x. And so we have f of x. The goal here is to sketch a graph of f prime. Now, the first things that I would look for in this graph is I would want to try to identify the extrema of the graph. So specifically, I notice at this point and at this point, I've got a maximum and a minimum of f. And I know that if I were to draw little tangent lines here at these points, that the slope of those tangent lines is 0. So I would expect that at that x value for f prime, that the graph for f prime of x, which here I'm graphing in black, is going to have a height of 0. It's going to have a y value of 0 since the slope of the tangent line of f is 0. Now from there, what I'm going to look at is I'm going to look again at the slope of f. So in this case, we notice that over time, we see that the function is increasing, then decreasing, then increasing again. And we notice that even on the parts where it's increasing, the slope is changing, right? It's steep here, it's maybe less steep here, it gets to 0, and then we can continue sort of talking about the steepness here. One way we can think about this is we can say, okay, all the way over here, on the left side of the graph, it is very steep. I'm going to put a large plus sign here to represent that. And we notice that as it gets closer to the horizontal tangent line, it still has a positive slope, but it is less steep. So I am going to put a large plus sign here to represent the steep, like a very positive slope, and a slightly positive slope here. And what we notice is that it gets slightly, over time, it gets less and less and less steep. That very positive slope is getting smaller and smaller and smaller until it hits 0. And so I'm just going to represent that with like decreasing sized plus signs. So it has a positive slope. It's very positive. It's still positive, but it's getting smaller until it gets to 0. Then we notice that the graph has a negative slope on this part, right? The graph of f has a negative slope, which starts off sort of small and gets a little bit steeper. And then it gets a little bit less steep over time. So this point right here, that x value is the steepest. And so to me here, it's slightly steep, it gets pretty steep, and then it's leveling out towards a horizontal slope of 0 here. I'm going to then take a look at this next part where we see that it's increasing. Again, here, what I'm noticing is that it starts off with a slight positive slope, and then over time, that slope is getting steeper and steeper and steeper. So as the x values increase in this direction, we notice that it is getting more and more positive. The derivative is getting more and more positive. So given what we see, I think I'm going to switch here to a very bright color. How about like hot pink? We've got these 2 points here, which we identified again because of the extrema, right? We know that at these 2 points, the slope is 0, which means the derivative needs to be 0. And I'm going to highlight f prime of x here in pink. So what we see here is that we have a very positive slope. So I'm expecting something with a y value that's very positive, and that value is going to still be positive, but get closer and closer and closer to 0. So I'm thinking of something like this. So it is very positive. So the slope is very positive. So we're up here. It's still positive, but it's less so. It's still positive, but it's less so. It's still positive, but it's less so. All the way until it hits 0 when it has a slope of 0 here. Then we notice that it starts off slightly negative, gets more negative, and then slightly negative again. So in this case, we're going to have something like this. And then after that, we've got something that's slightly positive, but getting more positive. And so that function is maybe going to look something like this. So this graph here in pink is what I would expect f prime of x to look like given this function. Now, it's not an exact science. Because, especially since I'm sketching this graph, I don't know exactly how, as precise numbers as to how steep it is. And so numerically, I can't say, but we can get the general shape of the graph. The only things that I know for sure are the points where there's horizontal tangent lines that I would expect to see sort of these in the exact same x values when I'm sketching that graph. Other than that, we're just sort of paying attention to how steep the graph is, whether it's increasing or decreasing, and then therefore whether the derivative is positive or negative. One thing that I think that's also like really interesting to notice, if we think about our parent functions, we know in general, thinking about our parent functions, that a graph of this shape that we see here, this looks very much to me like a cubic function. It sort of has that disco dancer style shape. The original function f of x had this sort of cubic function, right? It's cubic, which is a family that has like the x cubed, and they generally look like this. We would expect if the original function was an x cubed function, if you were to take the derivative of it, if we even just think about the power rule for it, we would have a quadratic. Maybe in this case it would be like 3x squared, but it wouldn't be in the family of the x squared function, which we would expect quadratic functions to look like a parabola. So if we think about parent functions and just the way that they interact, we would expect that if we had some sort of cubic function, that the derivative would look more like a parabola. And we can see that that's the case when the original function was here as a cubic. Our derivative function ends up looking like a parabola through those 2 points. Sometimes you can use that extra parent function information to help reason and make sense. Similarly, if I were to ask you to take the second derivative and to sketch that, we would think, okay, well, we've got a quadratic function for our f prime. If we took the derivative of that, we would have like 2x, which is of the form of just a linear function. And so I would expect the graph to maybe look something like this, like a straight line. If we took the derivative of a linear function, maybe I would expect, if we took the derivative of that, it would be a constant. So maybe just like 1. So we would have a constant function, and I'd expect the derivative of that to be a horizontal line. So sometimes we get, lucky depending upon the problem. Maybe it's a nice parent function like this, and we can sort of anticipate what the derivative is going to look like. Obviously, you want to be able to reason using the slopes and thinking about tangent lines and how steep they are, because sometimes they're going to give you graphs that are strange. Maybe it's not just a parent function, or maybe it's like a piecewise function, and there's going to be different parts to it. In that case, you have to really rely on this. Is the slope positive? How positive is it? Is the slope 0? Is the slope negative? And then just trying to sketch that out by hand. Let's take a look at this other one. Now, they're changing this up. Now, obviously, the graph that they're giving us is the same, right? We see this cubic function that we've got here. But in this case, now they're telling us that this is f prime of x, and we're trying to go in the opposite direction. We're trying to think about what would the original function f have to look like. In this case, we've got a couple of things that we would want to emphasize based on what we know from chapter 5. Specifically, what I'm going to focus on when I'm sketching f from f prime is I'm looking for places where the derivative is 0. So I'm looking here and here and here. Now, the reason why we care about that is because those are our critical values. Right? There are critical values for our graph, and we know that critical values from earlier in this chapter are places where f of x may have a maximum or minimum. So f of x may have a max or a min. And so those are useful places for us to notice. So what I'm going to then do is I'm going to take a look and I'm going to think about what the sign of this function is telling me. Specifically here on this interval, I'm going to just sort of highlight these into to some parts. So I'm going to highlight this. I'm going to highlight this. I'm doing this in red. And then I'll highlight these parts here in green, these segments of this graph. Now, this first part that we've got here in red, we notice that the derivative is negative. Right? The fact that the derivative is negative on this segment, that means that for every x value for the f of x function, it has to have a negative slope on that interval. So I would expect, because of this, that this is telling me that f of x is decreasing on that interval, on those x values, up until it hits this point. Then we know, essentially from over here, this green part, that f of x is increasing because the derivative is positive. And I'll put that over here on this other green part. We know for both of these green parts that f of x has to be increasing because the derivative is positive. And for these two red parts that we've got here, we know that f of x needs to be decreasing because that derivative is negative. Right? Again, we're sort of really tying in a lot of the information we learned earlier in chapter 5 into this graphical interpretation of the derivative. What else do we know from our information earlier in chapter 5? Well, we see at this particular x value right here that the derivative is changing from negative to positive. We know from our work earlier that that tells us that this x value is going to be a minimum on f of x. Similarly, that's going to be true for this one over here as well, because the derivative is switching from negative to positive. It's changing signs through that critical value. We also notice that this point here in the middle is switching from positive to negative, and so that's telling me that there's going to be a max at that x value. So, with all of that information here, I'm going to leave all of this text here, which might be a little bit in the way, but I want to be able to see what we've got. Again, we are expecting a minimum. So at this x value, I'm going to just draw sort of a low point on the graph. This is going to be the minimum, my f of x. And again, here in pink is going to be my f of x function for this problem. Then at whatever x value this looks like 0. I'm expecting there to be a maximum, so let's put that right there. That's a point that's high on the graph. And then I'm expecting a minimum at this x value again, so I'm going to put that here. Now, what I'll say is this is, again, not an exact science. I don't know how high or how low this point is. I just know it's a minimum based on whatever's going to be around it. I know that this point's going to be a maximum based on what's around it, and this is going to be a minimum based on what's around it. We also know that to the left of this point that we've got right here, this x value that we've got right here, the derivative is negative, and so f of x is decreasing on that. So I'm going to start over here, and we're going to decrease into that minimum value. So it is decreasing. When we're looking from left to right, it is going downwards. It has a negative slope, just like since f prime is negative. Then we see from this x value to this x value that the derivative is positive. It's got a positive slope, which means I'm expecting the function to increase up until that max up here, at which point the derivative from this x value to this x value is negative, right? It's negative. So we're expecting then the function to decrease until it hits that minimum, at which point then at this x value, the derivative is positive again. So we're expecting a positive slope after that point. So here in pink is what I would expect this function to be, sort of looking like this shape. And once again, like especially going in the, what I'm going to lead into is this idea of an antiderivative. But when I have f prime and I'm trying to find f of x, finding the height of these values is not exact. If I were, for example, grading this problem, I would just be looking to see at this x value, do you have a minimum on your graph? At this x value, do you have a maximum on this graph? At this x value, do you have a minimum? And then is your function increasing and decreasing in the appropriate intervals? Beyond that, maybe this is a little bit lower, maybe the whole graph is a little bit lower, but that is what we're looking at when we're grading problems like this. Going back to our idea over here about the parent functions, taking a look at this pink graph, we know that the derivative was a cubic function. So I would expect, what would give us a derivative of a cubic function? It would have to be something like an x to the fourth function. So maybe like a quartic function. And in those cases, those look sort of like parabolas, but they sometimes have these little bumps that look like this. And so this makes a lot of sense that the original f of x function would be a quartic function, or a graph that looks like a quartic function, given that the derivative was a cubic shape. All right. That is the written part for this. We're going to switch over now to the calculator part. As we had said on the calculator section of the AP exam, we are expected to be able to graph functions. So we're going to be working on that graphing calculator, specifically on how to take the derivative of sine of e to the x. And we're going to talk about it numerically, and we're going to talk about it graphically on the calculator. So we're going to switch over now, take your calculators out, and let's continue those notes. All right, so we've got our graphing calculator app open. As we had said, we're going to be trying to graph both numerically and graphically. So I want to remind you, using your graphing calculator TID3 or TID4, that you are able to take the derivative of a function numerically at a particular point. And so the way that we do that is we hit the math button, and we go down to this number 8 under the math menu that says n-deriv. So it stands for a numerical derivative. And the goal here is that you're taking the derivative at a particular point. And so if we hit that 8, it comes up in this TID4 with this nice math print formatting where it's asking us the derivative with respect to what variable. So if I say the derivative with respect to x, in this case we'll use the function sine of e to the x. So sine of e to the x. I'll put that x in that exponent, close these parentheses, and actually move over before I do that. So that's all the way closed. And then here, if we're trying to have the calculator estimate the derivative at a particular point, we can put what x value we want. So let's say we want the derivative at x equals 3. So you can put 3 in here, and then your calculator will do this numerical derivative. And we can see that it's about 6.599. Now, obviously, sine of e to the x is a function that we could do the chain rule on, and this is a function that would be absolutely fair game for you to do by hand on the AP exam. But sometimes they're going to give you functions that we actually can't use. We can't do our chain rule, our quotient rule, our product rule. They're expecting you to be able to use the calculator to find those derivatives. And in those cases, if it's the calculator section on the AP exam, you are welcome to use this to find the derivative at a particular point. So a reminder that exists. Again, that is under the math and 8 for numerical derivative for this. Now, in addition, your calculator can actually sketch the derivative of a function as well if we tell it a particular thing. So in this case, let me actually just check to make sure that I'm in radian mode. Hey, I am. Great. We can go to the y equals screen, and what I'm going to do is I'm going to put the function in sine of e to the x, so sine of e to the x, and I'm going to close those parentheses. It's doing that in the exponent, so let's move to the side here and close those parentheses. So if we graph this function, I'll just do a standard zoom for right now. We can see that this blue line that we've got is sort of oscillating back and forth, which makes sense because it's a sine function. So I'm going to change my window just so I can see that real quick. Let's go to the y value. I'll just take a look at the positive x values from 0 to 10, and then we'll change the y min and y max to -1 and +1, respectively. I'm doing that because I know that the output of a sine function is always between -1 and 1. And so if we graph this, all right, we have this graph that's sort of going crazy. It's going back and forth and oscillating all over the place. But let's actually, I'm going to change the window some more because this is a lot of graph. Let's just look between x equals 0 and x equals 3. I think that's going to make this a little bit easier to see. Okay, So we have this function's going up, it's sort of oscillating back and forth. Now, what would the derivative of this look like? If this was a function that I couldn't take the derivative of by hand, my calculator can help me sketch the function if I know what the equation of the original function is. So I'm going to go to y equals, and what I'm going to do is I'm going to hit the same math 8 that I hit before. I'm going to go to the math menu, and I'm going to go to nderiv again. Now in this case, I'm going to have it take the derivative with respect to x. In here, where it's asking for the function, I can either type sine of e to the x in again, or I'm going to just have it reference the first y equals function that we've got here by going to the variables button, going to y variables. I'm going to hit the function, I'm going to hit enter, and then I'm going to have it pick the equation that's in y1. So this is going to take the derivative of whatever I have in the y1 equation. Now again, if I don't want to do it that way, I could just type sine of e to the x here as well, and it would do the exact same thing. Here is the only part that's really different. Instead of saying to take the derivative at a specific value, I'm not going to put like x equals 3 because I want it to actually calculate the derivative at every x value on here for the graph. So instead of putting a number here, I'm going to actually say when x is equal to the variable x. And so as the graph is going on, it's going to calculate the derivative at every single one of those points and give a sketch of what that graph is going to look like. Let's see what that looks like here. So in blue is our original function, and in red here is our derivative. Maybe I'm going to zoom or do a slightly larger window. So let's go from like -5 to 5, just so we can see this. Again, here in blue is the original function. Our red here is our derivative of that function. Let's make sure this makes sense. Well, we see that it's got a positive slope. This blue value, if we drew tangent lines, looks like it has about a max about right here. And we notice that the derivative, it has a positive, it's positive and then switches to negative going through that point, which makes sense that there would be a max at that point. Then we see that at around right here, there's a minimum on the original function. And accordingly, we see that the derivative is going from negative to positive, going through x equals, or rather, the output is 0 at that point. And we can see at each of these maxes and mins of this function that the derivative is 0 here. We have these critical values that sort of line up exactly with where these maxes and mins occur. So this is a really powerful thing. Again, going back to the y equals, we can put y2 or any of the other y's as the derivative of the original function. And again, you can type the function in itself or do this like vars way of bringing that up. That's a nice shortcut that our calculator can do. Again, it's really useful on the calculator section of the AP exam. Let's go back to a regular lesson. All right, now that we saw the calculator part, we're going to wrap up this lesson. So as a reminder, we've got practice at the bottom of the sheet. I've posted the solutions as well. Good luck on your mastery check, and have a great rest of your day.